Hi, my name is Arvin Farid, Professor of Civil Engineering at Boise State University, and I'm going to talk to you about electromagnetic waves for geoenvironmental applications as part of the Research to Practice video initiative by the GI. These are for research articles we published related to this presentation, and you can refer to them for more details, as well as other references used for this presentation. The first application that I will briefly talk about is non-destructive geophysical techniques. They use different types of waves to detect anomalies within a background, and they work when there's a contrast between the properties of the background and the anomaly. And by properties, I mean the ones that govern propagation of the wave. For example, seismic waves are governed by density and various strength moduli. Electromagnetic waves, on the other hand, their propagation is governed by electric and magnetic properties and through Maxwell's equations. And there are different modalities that we could use electromagnetic waves and methods we call radar-based techniques. One very popular modality is a surface reflection modality called ground penetrating radar, or GPR. Another one is a cross-borehole radar modality, which is more useful for deep detection. EM waves have been used to detect contaminants, tunnels, landmines, and etc., or characterize soil's moisture content, density, salinity, electrotypes, or mineralogy. And when it comes to soils have very complex dispersive properties. Dispersive means their properties are a function of frequency, which, by the way, provides a lot of versatility for radar-based methods. This table shows various material from PCE to water and dry or saturated soil at different frequencies. You could see relative dielectric permittivity or dielectric constant, otherwise known as dielectric constant, or electric conductivity, their values at different frequencies. And you can see soils are dispersive. As any other method, electromagnetic waves have their own limitations. For example, material that have high dielectric permittivity or high electrical conductivity are lossy or absorb EM energy. Hence, the penetration depth of electromagnetic waves would be limited to soil properties and hence frequency dependent. A measure of penetration depth for EM waves is skin depth, which is basically the distance traveled before the EM energy is attenuated by a factor of 1 over E, or by 37%. Basically a loss of 63%. For example, a gigahertz surface reflection method such as GPR does not penetrate anything more than, let's say, 10 to 50 centimeters into a lossy soil such as clay, but lower megahertz EM waves could penetrate 10 to hundreds of meters into the soil. So far we talked about geophysical detection and characterization. In terms of remediation, electromagnetic waves have some advantages over some other methods, and obviously their own limitations. For example, in electrokinetics, direct current or DC has been used for remediation. AC, alternating current, has also been used, but both DC and AC generate a lot of heat, and DC only mobilizes charged particles, and DC also changes the pH, both the heat and the change in the pH could be harmful to the microbial populations responsible for biodegradation. As opposed to that, we picked electromagnetic waves, and due to various relaxation mechanisms and how electromagnetic waves impact larger to smaller particles at various frequencies. We could pick the right frequency and power level not to generate a lot of heat. And in addition to charged particles, we could move neutral particles that are either polar or non-polar. And we applied that method at the lab scale to show that neutral nonpolar contaminants or contaminant simulants, such as organic contaminants, could be removed using electromagnetic waves, as well as even the zone of influence of air sparging could be controlled and enhanced using electromagnetic waves. And as you may know, air sparging is limited to the initial zone of influence that's formed, and the only solution, or the most popular solution that currently exists, is pulsation of air pumps, which is pretty time consuming. In terms of the fundamental theory and what helps us use electromagnetic waves for the purposes we mentioned, the force behind this method is a force called dielectrophoretic force, and the phenomenon is called dielectrophoresis. Dielectrophoretic force is a force that is applied to any particle within a background where there's a contrast in the dielectric permittivity of the two, and it's a function of size of the particles, the properties of the particles in the background, and any gradient in the electric field. This was used in electronics manufacturing in the past, but we demonstrated that it could be used for geotechnical and geoenvironmental applications as well. Here you see three images of the same box. It's a resonant cavity that you can see through. At the center, there's a cup that we inject, where we inject a dye denser than water to simulate DNAPLs, dense non-aqueous phase liquids. Upper corner of the box, there's a loop antenna to magnetically stimulate the box and excite and create electromagnetic standing waves. The left image shows no electromagnetic waves, hence the dye, being denser than water, starts sinking down like DNAPLs. The central image shows an excitation at 65 megahertz with only 10 watts of power. 20 or 30 watts were also tried, and the dye moves upward. And then the image on the right is at 75 megahertz. Only 3 watts of power was sufficient to contain the dye at the center where it was released. So the central image is a remediation case. The right image is a containment. And the reason 65 and 75 megahertz cases are so different is because the electric field pattern was different, hence the electrophoretic force pattern was different. And the pattern for 65 megahertz creates an upward dielectrophoretic force, and the pattern for 75 megahertz creates a force that's toward the center. Also, we showed that EM waves work on air sparging, and they control the zone of influence. Here you see three images of a box full of saturated glass beads. The center of the box, there's a pipe to pump air into the box. The image on the left shows the box before the air was pumped. The image at the center shows where there's no electromagnetic waves and the air was pumped, and an axisymmetric circular zone of influence was created at the up top. And the image on the right shows where we applied a certain pattern of dielectrophoretic force using electromagnetic waves to create this lip shape zone of influence. And we analyze this image and measure different characteristic properties of the shape of the image and the area of the image. The pattern And the shape of the zone of influence is governed by the dielectrophoretic force field pattern, as you can see. And the area was also analyzed at different powers. Here on the bottom left, you can see an image where the vertical axis shows the area of the zone of influence, and the horizontal axis shows the EM power from 0, no power, to 10, 20, 25, and 30 watts. And you can see the area can also be controlled. When you design any method, you got to be careful about the side effects. And we realize electromagnetic waves alter the hydraulic conductivity of any soil. In the case of sand and silt, EM waves increase the hydraulic conductivity. We discovered the relation. And in the case of, and you can see how discharge on the vertical axis increases with the increasing EM waves power, RF power, radio frequency power. And in the case of clay, hydraulic conductivity decreased, and we discovered the governing equation for that as well. And as you can see, the discharge decreased with increasing power. And in this equation, K is the saturated hydraulic conductivity, and K prime is the electromagnetically stimulated saturated hydraulic conductivity, where S is the power density, A is representative area, and alpha and beta are constants that are a function of the soil type and the EM frequency. With that, if you have any questions, please reach out to me or to the GI website. Thank you.